Okay, so here we are. We're going to be talking about polarity today. Distribution of the electrical charge on the molecules. It's based off of the Lewis structure, which is based, then you figure out the shape. So we'll be looking at this today and then adding on intermolecular forces here at the end of this video. Okay, so before we can get into molecular polarity, we need to talk about bond polarity. Okay? Now, last unit we talked about ionic covalent metallic bonds. Those are full out bonds here. Now we're going to break down the covalent bonds into a couple different categories. So, ionic bonds have an electronegativity difference of that is greater than 1.7. Okay? So, electronegativity difference is greater than 1.7. However, we said if it was 1.7 and less, then it was going to be covalent. Now we're going to give you a couple ranges in the covalent in terms of bond polarity. Covalent bonds, as it says here, can be not a nonpolar or polar. So nonpolar covalent bonds are formed when there is an equal sharing of electrons. So the distribution is pretty much evenly spaced out. And the electronegativity difference is less than or equal to 0.4. Less than or equal to 0.4. Polar covalent bonds are formed when there is an unequal sharing of electrons. And the electronegativity difference is greater than 0.4. So basically what we're talking about here is polar covalent bonds go from 0.5 to 1.7. This is our range, okay? Now, 0.5 is considered like slightly polar, whereas 1.7 would be considered extremely polar. So this one's going to be slightly, whereas 1.7 would be like extremely polar. Okay? Extremely polar. So it is a range. And like I said, 1.7 would be like the greatest electronegativity, which would be the most polar bond. 0.5 would be the least difference, so that would be the least polar bond. Now, the atom that is more electronegative will pull the electrons harder and typically has a partial negative charge. Now, electronegativity, I gave you the values on your little chart, but they're also going to be on the next slide. The most electronegative element is fluorine. Remember the trend, if you go up and to the right, the electronegativity increases. So, we're looking for which out of our pair of atoms in the bond has the higher electronegativity to be assigned the negative charge. The other one that's less electronegative is going to be assigned the partial positive charge. Now they use these funny symbols, okay, for the partial charge. This little that wasn't very good. Hold on a second. It's like a squiggle with a circle here. That is called a lowercase delta. It's a Greek symbol, whereas the uppercase delta is like the triangle, okay? But we assign the partial charges when there's an unequal distribution of electrons. So if I'm looking at these two examples here, this is hydrogen with hydrogen. This is hydrogen with fluorine. So H2, and this one's HF, okay? As you can see, H2, everything's nice, equally distributed. That would be a nonpolar covalent bond, okay? Nonpolar covalent bond. Whereas HF, if you look here on this side we get more electrons over to the F side. F is more electronegative. So we would assign this side to be the partial negative. Over here by the hydrogen would be the partial positive. We also use this red arrow thing. This is called a dipole moment. And the arrow points towards the more electronegative side. So here, like the end, it looks like this little cross at the end, which is supposed to be like a positive. So you would point it towards the fluorine. The cross end would be over here by the hydrogen. The arrow part, grab gonna do it in black so you can see it better. Like so, would point towards the fluorine because the fluorine has more electronegativity, and the hydrogen would be the positive side, like so. Now we're going to calculate electronegativity and decide on the type of bond it has. So the first thing you need to do here is look at your bonds and then look at their electronegativity values. I did print off a larger one for you to have picked up on your way in. Okay, so if I'm looking at this first bond, right here, okay, we have carbon, carbon's 2.5. We have sulfur, which is also 2.5. So if I'm calculating this one, this is going to be 2.5 minus 2.5 gives me 0. Right? Now I calculate the next one here. Here I have the sulfur, which is 2.5, but I also have fluorine. Now you always subtract the smaller number from the higher number. So this case, I would do 4.0 minus 2.5 gives me 1.5. Right? Then I would come over here, look at, I have N, and I have F. So 4.0 minus the 3.0 gives me 1.0. Like so, we're just looking for the difference between the two numbers. And last but not least, here's boron, and then here's hydrogen. So it's 2.1 minus 2.0, like so, and this difference is 0.1 difference. So we have our values here, okay? And they want us to rank from least polar to most polar. So which one was our lowest electronegativity difference? CS. So this is what we would put here. Now, the other thing we have to identify, is it polar covalent, non-polar covalent, or ionic? So if it has a 0 for electronegativity difference, which category does it fall in? Non-polar covalent. So non-polar covalent. Like so. Which one would be our next one?
BH.
B to H. Good. And which category does that one fall under? Also non-polar covalent. Because it is less than 0.4. 0.4 or less is non-polar covalent. The next one is N to F. Right? And the difference is 1.0, so which range does that fall in? This one's polar covalent, very good. And last but not least, we have S to F, which is a difference of 1.5, so this one is also polar covalent. Like so. Now, it does want us to use, for the polar bonds here, the dipole moment to point the direction. So, out of my two polar bonds here, these were the only ones that we would apply the dipole moment to. So, which one's the more electronegative element? Gonna be fluorine, so they're both gonna point towards the fluorine, like so. Okay? So now, it's gonna be your turn to fill it out. Your turn. So let's go ahead, take a moment to do those calculations in practice.
All right, now.
All right, so calculating our electronegativity differences for our four bonds over here, as you can see. Remember, once again, take the larger number, subtract the smaller number to get your difference. So out of those, which one is going to be the least polar?
Zero.
The carbon-sulfur bond here, C to S. Its difference is 0, so that makes it non-polar covalent, which we're going to abbreviate NPC because I want to abbreviate. All right. I know I don't mean the non-playable character, even though that's kind of funny in gaming and all that. All right. Next one is going to be C to H. That's a difference of 0.4, so that still keeps it as non-polar good. And PC. Now, coming up next is N to O, which is 0.5. So that one is barely polar, but it does make it under the polar mark because polar has to be 0.5 to 1.7. So it is slightly polar. Okay. And our last one is BE to O. Now, this one's a bigger difference than 1.7. So what category does that put it in?
Ionic.
This is ionic. So this is not a not a covalent bond. It is a full transfer of electron. It is a full charge kind of deal here. However, we still need to label our polar. So out of N and O, which one's more electronegative?
Oxygen.
Oxygen. So we're going to point the arrow towards the oxygen and put on the dipole moment. Okay? So you will be expected to calculate electronegativity differences with the table. We do not expect you to memorize the table, but you will be provided the table on the next test or quiz. Alright, so now let's talk about molecular polarity. If you have ionic as your bond type, you automatically have an ionic compound. Okay? This is an ionic compound. It is not going to be covalent at all. You have a full transfer of electrons. You have full charged particles like Na plus, Cl minus, that forms NaCl. You have the metal, non-metal kind of deal, just like we went over last unit, okay? However, if you have nonpolar covalent bond types in your molecule is automatically nonpolar covalent. Nonpolar. So, if all your bonds in the molecule are nonpolar, it renders it completely nonpolar. This is where it gets a little crazy, though, on our polar covalent. Okay? If you have polar covalent bonds, you can have one of two types for your molecule type. You can have nonpolar or polar, depending on what we call the shape here. Now, why is shape important? We're going to talk about that right now in just a second. Electronegativity gives us the bond type, but the shape tells us the overall molecule polarity. So, looking at the individual bonds and also looking at the symmetry of the entire molecule. Symmetry means it has to be like the same on all sides. You can evenly cut it in any direction. If it's symmetrical, basically, it ends up being nonpolar. So let's look at some of these examples. Nonpolar molecules are indicated by a symmetric molecule. So you're looking for symmetry here. And basically, what does that mean about our central atom? Once again, this goes back to looking at the central atom. No lone pairs, same outside atoms. This is on the central atom. Okay? If there aren't any lone pairs in the central atoms and the outside atoms are the same, it's automatically nonpolar because it will be symmetrical. So, like for example here, this BF3 molecule, if we cut it this way, it's the same on both sides. If we cut it this way, it's the same on both sides. If we cut it this way, it's the same on both sides. So that is a very symmetrical arranged molecule. Alright, now for polar, what you'll see, lone pairs on the central atom or different outside atoms. Okay? We call this asymmetric, where it's not symmetrical. Okay? So if you see lone pairs on the central atom, for example, H2O, we all know H2O is polar anyways, but it's because it has those two lone pairs. You can cut it this way, but if you try to cut it this way, it is not symmetrical. Okay? So, this one right here too, where you have only two atoms in the molecule, if you cut it this way, sorry, you can't see that one. If you cut it this way, different on both sides, purple one, gray one, that is not symmetrical. Okay, so lone pairs throw off the symmetry, but if you have different outside atoms, that throws off the symmetry as well. Alright, so now we're going to practice by looking at the Lewis dot structure. So we're looking over here at ammonia, NH3. Okay, we can cut it this way, but can we cut it that way? No, so this one's automatically polar. This one's polar. It is asymmetric. It has a lone pair on the central atom. Ca for central atom. If we look here at F2, this is F2. Cut it down the middle. Is it the same?
Yeah.
This one's nonpolar because it is symmetrical. Symmetrical. You can evenly cut it. Okay? Now let's try the next ones and you tell me. We have HCl over here. Yep, this is polar. Once again, this is asymmetric. And if we look at this one where we have CH3F like that, first of all, what shape is that one? Tetrahedral, good. We have 4 bonded, no lone pairs. You cut it this way, not symmetric, right? So this one's also going to be polar. Okay? Asymmetric. Outside atoms are not the same. We have 1 F and 3 H's, so the outside atoms would not be the same. Alright, so, like you're going to have to do on the quiz, we have to draw it first. Then we can determine whether it's polar or nonpolar. So if I'm looking at our molecule here, that is BH2Cl, what's going to go in the center? B. How many electrons does B get? 1, 2, 3 is correct. Now, I'm going to put the other ones around it, like so. And then I'm going to put the dots in here. How many dots does hydrogen get? 1, very good. How many dots does the chlorine get? 7. And I strategically place them so they all face inward towards the open one faces inward towards the boron. We connect our dots like so. Right? So we end up with now you tell me, is that polar or nonpolar?
Or polars.
Good, because it's not symmetrical, where there's chlorine on one side, the hydrogen on the other side. Therefore, this one is asymmetric. Asymmetry means it's going to be polar. Very good. Thank you very much for pointing that out. All right, moving on to silicon dioxide. So we have our S in the middle. How many dots does S get?
4.
2, 3, 4. Strategically place my other ones on opposite sides here. Oxygens get 6. And I leave them open towards the center. This one's going to form what? Double bonds, right? So we get Si connected to our O's here, like so. What shape is this one? Linear. So this one, if you look here, if we cut it down the middle, this one should be nonpolar. It is symmetrical. There aren't any lone pairs on the central atom. That is correct. Very, very good. All right, now we're going to go into forces. Forces, nice section on forces, okay? Before we get to truly going into all the intermolecular forces, we're going to talk about how an intermolecular force is different than an intramolecular force. The prefix intra means that it is within, inter means between.
So between molecular forces.
Okay. Intra means within. You'll see it over here as like a bold line between the atoms. This is a connection between the oxygen and the hydrogen in our molecule, within the molecule. you'll notice over here the interforces are noted by dotted lines or dashed lines. They are weaker, and they are between the molecules. Now, the between ones is what we're really looking at here. The bold ones, those are what we would consider full-out bonds, like metallic, ionic, or covalent bonds. These ones are going to be between molecules, and they're weaker than the full-out bonds, okay? Now, intermolecular forces depend on the polarity. That's why we need to know if it's polar or nonpolar before we begin, okay? So, I like this analogy. This is a good way of explaining intra versus inter. If you look at this, this is HCl, hydrogen and chlorine together. So, the thread part right here, these are the bonds. These are the intra forces, like so. Whereas the Velcro, which is a little bit more easily ripped, okay? These are between the molecules, holding the molecules together. And these ones would be considered the interforces, or IMFs for short, intermolecular forces. Those ones are between and they're weaker. You can rip Velcro much easier than just trying to rip out thread. So it's a very good analogy in terms of strength, the difference between intra versus inter. Alright, so you could easily be given a diagram here, and like I said before, the red dashed line, which one is that one going to be? This one would be the intermolecular force, like so. Whereas the bold line here between the boron and the fluorine, that one would be considered intra, or a full-out bond. That would be a polar covalent bond. If you look at the electronegativity differences between boron and fluorine there, it would be greater than 0.5 and less than 1.8. Types of intermolecular forces. This one is not an intermolecular force, but I just want to remind you what an ionic bond is about. This is a full-out bond, ionic bonding. This would be considered intra. Held together by opposite charges, so you have full-out Na+, you have Cl-. They are attracted by the full charges. That forms the force between them, that electrostatic attraction. Now, if you compare ionic bonds to anything that's going to be an intermolecular force, it is always going to be much stronger. So that's why we call it the strongest force here, in comparison to any of the interforces. Now, London dispersion forces are the first type of intermolecular force. Molecules and atoms have LDFs. Anything that has an electron cloud in the covalent category is going to have London dispersion forces. Now, you can call them London dispersion forces. You can abbreviate them LDFs for short, or you can just call them dispersion. Any of those would be correct, okay? These are the weakest of all the three intermolecular forces. It's because they are temporary dipoles. Basically, as you can see in our lovely GIF over here, when the molecules are away from each other, the electron cloud is equally distributed. When they move towards each other, they distort the electron cloud. It shifts over, and it creates a partial negative side and a partial positive side, which is that temporary dipole. And this is the dominant force of all nonpolar molecules. So if the molecule is nonpolar, the only type of force it's going to have is London dispersion forces, or LDFs. One thing to note about London dispersion forces that are important, or dispersion forces, they increase and get stronger as the molecule gets larger. So as it gets larger, it gets a larger electron cloud. More electron clouds can shift. Larger electron clouds means more electrons can shift over, so it creates a larger temporary dipole. And we call that being more polarizable. The more the shift, the larger the shift, the stronger it gets. So the more polarizable it is, the stronger it gets. The next one is called dipole-dipole forces, okay? This one's medium strength, as you can see. This is always going to happen between polar molecules. So polar molecules, if you and you look at the shape and you know it's polar, it's automatically going to have London dispersion forces, but it's also going to have dipole-dipole forces, and the dipole-dipole forces will be its stronger force, okay? Basically, as you can see, this one's a polar molecule, so the partial positive, partial negative. This partial negative attracts the partial positive on the other molecule, and it kind of just extends it as you go. And you can see up here in our GIF that the partial positive, partial negatives are attracting. They're forming those dashed lines. They come in and out and can attach to one another. So they are considered medium strength. Last one is called hydrogen bond, and this is a misnomer. They call it a bond, and it's not a bond. Hydrogen bonds are really just a type of IMF. And I put that here, not an actual bond. It involves hydrogen, of course, so that's important, but not a bond. It is specialized to only 4 atoms and 3 types of bonds. Obviously, hydrogen bond should involve hydrogen. But you have to be H to F bond, H to O bond, or an H to an N bond. And you have to see those within the molecule. If you don't see H to F, H to O, or H to N somewhere in the molecule, it does not have hydrogen bonding. But, of course, the major one that everybody knows about that has hydrogen bonding happens to be water, because water has OH and OH, so it has 2 of them in there. So it has stronger forces. You know that water has unique properties because it has these stronger forces that hold it together. And these are the forces, like, for example, if you have a glass of water, what makes the water molecules stick to each other in the glass? Well, it's going to be the London dispersion forces, the dipole-dipole forces, and on top of that, the water's going to have hydrogen bonding, and the hydrogen bonding is its strongest intermolecular force. So when we ask these questions, we don't ask you to usually list all of the forces. We just usually ask you to list the strongest force it has. All right, so we have this nice flow chart for you. Flow chart shows you, first thing you should ask yourself, is it polar or nonpolar? If it is nonpolar, the only thing it can have is dispersion force, or LDFs. This is the only thing it's going to have. If it is polar, though, then you have to ask yourself, do you see H to F, H to O, or H to N? If that's a no, it's going to only have dipole-dipole forces in addition to the London dispersion force. So the dipole-dipole force will be its stronger force. However, if you do see, it does have H bond, H to F, H to O, or H to N, then in addition to the London dispersion force and the dipole-dipole force, it will also have hydrogen bonding, and that will be its strongest force. Now, practice here. We could give you a diagram like so. First thing you should ask yourself, is that a polar or nonpolar molecule?
Or polar.
Polar. If you look at the central atom, the S has 2 lone pairs. You also have these that are dead giveaway. Partial charges. When you see partial charges on it, that automatically means it's polar. So, this is polar. What would be its strongest force based off of what we see up here? In order to have hydrogen bonding, it has to have HF, HO, or HN. Does it have any of those? No. So this one, the strongest force it's going to have is dipole-dipole. That's the strongest one shown in that particular one. Now looking at this one. Is this polar or nonpolar? Nonpolar, Cl2, of course. So what is the only force it's going to have? Dispersion. So that one is, because this is nonpolar, it's very symmetrical, right? Cut it down the middle. And it's only going to have dispersion forces. Haha, this one's kind of interesting because there's 2 different aspects to it. So let's check out the right over here. We see this in the molecule, O to H and O to H. What does that indicate to us? Possible hydrogen bonding. So, if we're looking at it, we see the O part going to the H part over here. That jives. This one would be hydrogen bonding. Like so. And this partial negative up here is going to attract that partial positive on that H. However, if we look at this other side over here, though, the O is being attracted to the partial positive on the C. So in that particular case, that one should be dipole-dipole. Very good. And you can abbreviate it dip-dip if you want to. But because it's not attracting over here to the H, it's only attracting to the C, still polar. As you can see, that is not a symmetrical molecule at all. That one's very asymmetrical. Very polar, but that particular attraction is going to be dipole-dipole, whereas the one that goes from the O to the H over there, that one's going to be hydrogen bonding. All right, so I have a couple of examples here to draw, and we have carbon here in the middle. How many dots does the carbon get? 4. 1, 2, 3, 4. We have 4 Fs, 4 fluorines. Going to put those around. How many electrons go on, or each, how many dots go on the fluorines?
7.
7. Good. Like so. And we would connect the dots. 1, 2, 3, 4. We have 4 bonds, no lone pairs. This is going to be a tetrahedral shape. Is that polar or nonpolar? No lone pairs on the central atom. Are the outside atoms all the same? Yeah, so this one's nonpolar. So, nonpolar means which is the only force it's going to have? Dispersion. So this one's dispersion. Okay? Because it's nonpolar. Dispersion. Now, this one right here, P. How many dots does a P get? Phosphorus. 5. 1, 2, 3, 4, 5. We have 3 hydrogens. How many does each hydrogen get? 1. Good. So if we connect these dots here, we're going to have 3 bonds. 3 bonds with 1 lone pair. What shape is that one? This one's T pyramidal, yes. Has the 1 lone pair on it, so is it polar or nonpolar?
Polar.
This one's polar. Now, it's polar, so which one is going to be its strongest force? Dipole-dipole, good, because it does not have HF, H, or HN, so it does not qualify for hydrogen bonding. So yes, this one would be polar, but it's still only going to be dipole-dipole. This last slide. Now, going to try to do this without drawing them. We have F2 here. Only 2 Fs. Is that going to be polar or nonpolar? Nonpolar, because it's just going to be F on each side. How about HF? Only 2 atoms again. We cut it down the middle. This one's going to be H on one side, F on the other. This would be polar. Very good. Now, my other question is, we don't really have to draw out the full one with SO2, but let's just consider S. How many dots does an S get? 6. 1, 2, 3, 4, 5, 6. So if I attach my oxygens to it, what's going to be on the central atom? 2 lone pairs. 2 lone pairs on the central atom means that one's going to be polar. This one's going to be polar. So, out of that, those 3, which one is going to be the least electron, or have the lowest intermolecular force or weakest intermolecular force? Going to be F2, because this one's only going to be dispersion, or LDF. Now, out of our 2 polar ones, which one comes next?
SO2.
SO2, because it is going to be polar with dipole-dipole, but it does not qualify for hydrogen bonding. So then this one, the HF, is going to have the strongest forces, because in addition to the London dispersion and the dipole-dipole, it has hydrogen bonding.